Hello, this is Dr. Liu. In this video, I will explain to you how to calculate work done by ideal gas. These are ideal monatomic gases. So let's start by drawing a PV diagram. This is a typical situation. We start with PV diagram, and we'll start with this process where the pressure is kept at constant, but volume is allowed to expand from V1 to V2. So now we have basically, let's imagine this was our ideal gas enclosed in this imaginary block. So here's our ideal gas, and at the moment it is equal to V1. It's going to expand, and we'll make it simple. We'll just make it expand in one dimension, such as going this way instead of expanding in all three dimensions. This makes it easier to track. So how much work is done? Well, that depends on how much force the gas can push, right? The force that the gas can push when expanding in one dimension should be equal to the pressure times the area of that dimension. This is the area, right? And this is the area A. And if you expand, I'll just draw expanded, very dramatic expansion here, adding more volume to the existing volume. Okay, so that's adding more volume. And the original dimension in this direction is x. So now you added delta x to that. All right. So now we know force, we know how much work is done. Because delta x is a small quantity, we'll also use delta w to describe a small amount of work done. This is not a full expansion into volume V2 yet. It's just on the way to from V1 to V2. So the work done is force times a small amount of displacement, delta x, just like I drew here. I exaggerated this increase of x just to make it easy to understand. So now we can replace force with pressure, area, and the dx. And area times dx is actually equal to dv, delta v, delta v. So the increase of the volume is due to the increase of the length at the same exact cross-sectional area. So you expanded, you got this much extra volume here. All right. So since we said P is constant, right? So pressure is constant due to this constant pressure process. We call it the isobaric process. So under this process, we can calculate the total work done. That is work done by the gas expanding from V1 all the way to V2, not just expanding a small amount, increasing small amount. This is the all the way. So that will be because the P here in our small amount of work is P, and it's still P because it's constant. And then the small change of volume is replaced by the more dramatic change of volume that we can see on the axis, right? This V2 minus V1. And if we look at the diagram, V2 minus V1 is actually this, right? This is V2 minus V1. That's the base to this height, which is P. So P is the height, and the V2 minus V1 is the base. So we're effectively calculating the area underneath this flat line here. All right, so this is actually area. So it's the area under the diagram. So that's for isobaric process. We have work done is equal to pressure times volume 2 minus volume 1. If you're expanding, then you're doing work as gas. You're doing work to the outside. If you're contracting, outside does work to you. So what about another process where V is constant? And this is iso volumetric process, iso and volumetric, so the volume doesn't change. And then if we see this volume doesn't change, then there's no expansion here, so there's no area underneath the curve because the base is 0. So we can imagine the base of the area is 0. So the work done is always 0 in this isovolumetric process. So what this process can do is, well, it could build up to a higher temperature, right, higher pressure, because you're going from one volume, the same volume, you will have to go up and down vertically in your state diagram. So then you probably go to higher pressure. At the same time, you go to a higher isotherm, so higher temperature, higher pressure. That's like a pressure cooker. Volumes kept constant before the release valve is actually pushed open. So that's that process. What if we have something a bit more arbitrary? Can we still use this idea, the area underneath the curve is the work done? And the answer is yes. So I'll have an example here, like this. So I'll mark these as this is volume in cubic meters. So this is 1, 2, 3, 4. And this is pressure in 10 to the 5th pascals, so 100,000 pascals. And roughly 100,000 pascals is atmospheric pressure, or the 101, right, 101 K. So this is 100,000, 200,000, and this is the origin where volume and pressure are both 0. So let's say we just start from this point. This point has pressure 200,000 and volume of 1 cubic meter. And then we go to the right, we decrease volume while and we also decrease pressure. Until then we maintain pressure and increase volume. Sorry, decrease volume, increase pressure, then maintain pressure, increase volume. So what is the work done here? Okay, so the work done here, now you see it's the area underneath this curve, and this is not a simple shape, so we can subdivide it into several shapes, more basic shapes, such as this area A1 here, right? This A1 is easy to calculate. It is a triangle, right angle triangle, and then this could be A2. This is just a bunch of blocks, a rectangle, right? So we can say work done is area underneath the curve, and the area has two distinct pieces, and A1 is a right angle triangle, so 1/2 base times height, and A2 is a rectangle, so base times height. Okay, so A1's base is actually this. So from 1 cubic meter to 3 cubic meters, so the difference, right? So that is equal to 3 cubic meters minus 1 cubic meter as a base, and the height is this minus that, so 200,000 minus 100,000, so 2 minus 1, 100,000, so that's the A1, and then A2, the base is this whole thing here from 4 cubic meters minus 1 cubic meter, so 4 minus 1, and then the height is 100,000, so 100,000, so the area, the total area is 3 minus 1 is 2, 1/2, that's a 1, 2 minus 1 is also 1, so 10 to the 5th power, and then we also have 3 times 10 to the 5th power, so 4 times 10 to the 5th power joules, or 400 kilojoules of work. just to take the gas from this process from the top left to the bottom right. All right, so the rest will be related to calculus. What happens if we're going through a different process where the pressure is no longer constant, and if the shape is no longer as simple? Well, for calculus, here is what we can do. We'll take this expression, delta work, small amount of work, finite, is P delta V. And we turn that into its differential format, dW equals P dV. So now we have infinitesimally small amount of work with infinitesimally small amount of volume increase. And then if we integrate that, the total work is dW, and we were going to expand from V1 to V2. We'll use them as limits, and here's P as a function of V because pressure now could depend on volume, dV, V1, V2. So that's the generic expression of work done by ideal gas. So we'll use a specific process to demonstrate how this can be used. So this process we'll use, say, T is constant. So isothermal process. Iso and thermal, so the temperature is constant. Okay, so in this process, because we're talking about ideal gas, we'll have PV equals nRT at our disposal, and T is constant, so it does not depend on volume, and pressure is equal to nRT times 1 over V. This is the function pressure as a function of volume, which will plug in here into the generic expression. So work done is equal to V1, V2 as limits. So pressure gets plugged in nRT 1 over V dV. So the constants factor out, and 1 over V dV integrates into natural log of V. So nRT natural log of V, and we have limits V1, V2, and if you plug it in, you get natural log V2, then minus natural log V1. The natural logs, subtracting two natural logs, you can have their arguments divided by each other. So that's a very useful relationship. So that's V2 over V1. The 2 is the final volume, and 1 is the initial volume. Okay. So one more process is adiabatic process. So in this process, Q is 0. So no transfer of heat, adiabatic process. In this process, we have a relationship PV to the gamma's power is equal to a constant K. And this gamma is defined as Cp over Cv. So Cp is constant pressure specific heat, and the Cv is constant volume specific heat. Okay, so with this process, P as a function of V is equal to K times V to the minus gamma's power. So work done is the same thing. We factor out the K, V1, V2, V to the minus gamma's power, dV. So V to the whatever power dV can integrate into, this is minus gamma plus 1 as a factor. This is just the inverse of derivative. So V to the minus gamma plus 1. Just imagine you differentiate this, minus gamma plus 1 drops out, just divides by this, the factor is gone, and you get minus gamma's power, right? So now V1 and V2. So if you just plug these in, so V2 1 minus gamma, that's the same as minus gamma plus 1, minus V2, V1, 1 minus gamma, and divided by 1 minus gamma. So this is how much work is done in an adiabatic process, imagining this process is happening at a very slow rate. Thank you.